I'm not going to really explain this. We're just going to accept it for now. I will be explaining it later. For a sample, so instead of doing a sigma, so sigma was the standard deviation of a population. The symbol for the standard deviation of a sample is just going to be a normal letter S. And the other thing that changes is that instead of saying mu, which is the mean of a population, we use x bar, which is the symbol for the mean of a sample. So it's essentially the same formula. The major difference is this -1 over here instead of just n. And what that does is it tends to very slightly increase the number. The bigger n is, the less of an effect it has. But if your sample is pretty small, then it has a fairly major effect. The next thing I'm going to touch on very briefly is something called variance. That's a symbol for variance, which might give you a clue as to the formula. And so the formula is the same formula as standard deviation, but without the square root. And I'm not totally sure what what variance represents beyond being the standard deviation squared, but when people publish things, they often give the variance as a measure of the standard deviation. So maybe it's a bigger number, which looks prettier. You could also have the variance of a sample, and the symbol for that is s squared, and that has the formula of this over n minus 1. So again, same formula, just without the square root. Example 3. So now what you have is we're going to have a frequency table. And we're actually not going to change very much. So we're going to start off, well, actually, before we do that, we need to figure out the mean. So the mean is going to be this times this plus this times this. It's going to be back to that, so it's going to be 82 times 3 plus 85 times 11 plus 88 times 12 plus 90 times 20 plus 92 times 4, all divided by 32, 46, 50. So that's going to be 82 times 3 times 11 plus 88 times 12. So that's going to, oops. Okay, so we have a mean of 88.1, and our n is 50, as we pointed out. So we're going to write our x values, and those are going to be 82, 85, 88, 90, and 92. Then we're going to subtract the means, so it's going to be the x values minus that. So that's going to give us minus 6.1, minus 3.1, minus 0.1, 90 minus 80.9 would be plus 1.9, 3.9. Then we're going to square these. So it's going to be 37.21. This one's going to be 9.61, 0.01, 3.61, squared is 15.21. And normally we would add these up. Ooh, we're coming off close to the edge of the page here, right? Normally we would add these up, but that's not what we're going to do here because we don't have the value of 82 once. We have the value of 82 3 times. So we don't have this deviation of 37.21 once, we have this deviation actually 3 times. And similarly, we have this deviation 11 times, and this deviation 12 times, and this deviation 20 times and 4 times. So what we're actually going to do is we're going to have to make an extra column where we're going to multiply those deviation squares by the frequency. And so what that's going to give us is 111.63. So 11 is going to be 105.71. So that's going to be 0.12. This one's going to be 72.2. That's going to be 60.84. And this is what we're going to add up. We're going to add up all these things. And then what we're going to get for that is we're going to get 569 plus 105. We're going to get 350.5, which means we can now finish this off. So the standard deviation is going to be the square root of 350.5 divided by n, and in this case is going to be the sum of the frequencies divided by 50. And that is going to give us 350.5 divided by 50. And that's going to give us 2.65.